Hello, student. Here is the second part. We talked about the spring work. Now let's talk about this slide. This slide explain two important concepts related to work, raising or accelerating a body. When a body is raised, the work done is equal to the change in its potential energy, like lifting an elevator. Similarly, when a body is accelerated, the work done is equal to the change in its kinetic energy. In addition to these mechanical forms of work, there are also non-mechanical forms of work, such as electrical work, where voltage causes the displacement of electrical charge, and magnetic work, where magnetic field strength acts on magnetic dipoles. Last one, electrical polarization work. It is one of the non-mechanical forms of work because it's involved in the arrangement of charges due to an electrical field, rather than the physical movement of objects or mechanical forces. Non-mechanical work like electrical polarization happens on a molecular or atom level and does not involve traditional mechanical motion. The benefit of this is that it can be used in various applications like in capacitors, which stored electrical energy. This slide, by the way, this figure related to the previous slide here. So they will talk about the elevator. We talk about the potential energy and the kinetic energy. So I don't know why they put it here in this slide. Anyway, so for this slide, the first law of thermodynamics, and I think all you know this law, which is provide a sound basis for studying the relationships among the various forms of energy and energy interactions. I think you all know the first law first law state that energy can be neither created nor destroyed during a process. It can only change forms. So the first law for all adiabatic process between two specified state of a closed system in the network done is the same, regardless of the nature of closed system and the details of the process. Like here, the increase in the energy of a potato in an oven is equal to the amount of heat transfer to it. So there is no change in energy. The energy in will be the energy equal to the energy out. Let's look at these figures, and it will explain the law very well. Again, I think I already explained the mathematical forms of let me call it mathematical forms of first law of thermodynamics, which is Q minus Q is the heat transfer, W is the work, equal delta E. So, which is the change in the total energy. So for this figure, if we look at if we apply this equation, so let's say there is when it says Q net, so there is Q will be Q in minus Q out, and for the work, let me write it like this. So oh, there is no work. So okay, the absence. Oh, okay, here they said the absence of any work interaction, the energy change of system is equal. So there is no work. So it will be Q n minus Q out equal the change of the delta, the change of energy of the total energy will be 12. So if this is if Q out is 3, so Qn will be 15. It just like an example to how to apply the first law of thermodynamics. Here it says the work of electrical done on the adiabatic system is equal to the increase in the energy of the system. So the work done on the system, so this will be negative, right? So the equation will be let's say delta E, sorry, equal to Q minus the heat transfer minus the work, and the work is already this is 0 because it's adiabatic, so there is no heat transfer, and the work is done on the system, so it's negative. So negative with negative will be plus, and it will be 5 kilojoule. So now you understand why how can we apply this the first law of the thermodynamics. Also, here's another example. It says adiabatic. So again, delta E equal Q minus work, and the work shaft done on the system, so it's negative. Again, delta E equal the work because it's adiabatic, so Q is 0, so we left with minus W, which is the work, and it's minus 8, so minus with minus will be positive, so it will be equal. So delta E will be equal to the work, which is 8 kilojoule. Okay, last example, same thing. It's adiabatic, and the work boundary done on the system, so this is negative, and again it will be equal to 10 kilojoule. Let's look at the slide. This slide talk about the energy balance, and it says the total energy entering the system minus the total energy leaving this system. And when you see the word total, it means capital E. So En minus E out will be the change in the total energy, and if it says constant, of course this will be 0. But let's look at this example in this figure. The energy change of a system during a process is equal to the net work and heat transfer between the system and its surrounding. So delta E will be equal uh, again Q, but there is like Q in and Q out, so the change of Q will be 15 minus 3, so in minus out and plus, if you still remember here, Q minus W, and this W is the work is done on the system, so it will be negative, so negative for negative will be plus, so 15 minus 3 plus the work, which is 6, the total will be 18. Here's again the equation, like how they converted to this form. So again, energy change of system delta E will be the energy at final state minus the energy at the initial, so the total energy, which is E. So if we have like this equation and we have final minus initial, final minus, and we can say delta U, so this is the internal energy, and delta kinetic energy, delta potential energy, and each delta means final minus initial, so we can come up with this form. So again, this form is same as this form, but it's instead of using final initial like this one, we use it like as delta. I hope this equation is clear, because this equation, let me erase here. This equation is very important. Now for this slide, the mechanics of energy transfer, which is En and E out. Energy balance for any system undergoing any kind of a process can be expressed more complicatedly as En minus E out will be equal to the delta E, but if it's in the rate form, if you still remember, when you have the dot, it's mean a rate. It's not like this one, it's like respect with time, but here it will be delta E over delta T. And if you still remember, if we have a steady state, this will be equal to 0. And for the constant rate, the total quantity during the time interval, delta T are related to the quantity per unit time as, and we have seen like this one, if the time is it's constant, we can use this one, and this is for the work if the time constant, and last one, this is the total energy of the time constant. The energy balance can be expressed on a per unit mass basis, and if you still remember, this is the small e, which mean it's per unit mass, and we have seen this form before. Again, energy can be transferred to or from a system in 3 forms: heat transfer, work transfer, mass flow. But if we have closed system, the only 2 things that can transfer from the system or inside the system will be heat transfer and work, because for the closed system, mass is constant. And if you see this equation, it says total energy in minus total energy out, And what's the forms of energy that we have? It could be heat transfer, it could be work, it could be mass flow. So heat transfer in minus heat transfer out plus, because it will be the total, work in minus work out plus mass flow in minus mass flow mass flow out. And this equation will be for a cycle. It's only for cycles, and we already explained the cycles in the beginning of the class. If you I have a whole cycle that will contain subsystems, and each system could be like compressor, could be a turbine, but the whole cycle will have all of these things. So for the work net for the whole cycle out will be the heat transfer net for the whole cycle in, or the rate of work net out will be equal to the rate of heat transfer net in. And we can see here, this is represent a cycle. If you this will explain this in chapter 3, which is the pressure and specific volume. It's called the BV diagram. And for this figure, we can see if we have control volume, which is open system, we can have mass in and mass out, and work in, work out, heat transfer in, heat transfer out. In this slide, we will discuss the energy conversion efficiency. Efficiency is one of the most frequently used term in thermodynamics, and it indicates how well an energy conversion of transfer process is accomplished. We can see efficiency is calculated as the ratio of the desired output to the required input. And we can see the example of water heater show that the efficiency is the ratio of the energy delivered to the house by the hot water to the energy supplied to the water heater. For example, high efficiency electric water heaters can achieve efficiencies of up to 94%, meaning that 94% of the energy supplied is effectively used to the heat water. When we talk about combustion equipment efficiency, we are referring to how effectively a piece of equipment like this combustion chamber. It's like in the car engine, when the fuel is burned, they call it combustion chamber. So the combustion efficiency is used on how much heat is actually delivered or used for heating process against the heat lost in the process, especially in the exhaust gases. The key part of combustion efficiency is to look at the heating value of the fuel. This tells us the energy released when a specific amount of fuel is burned. We have two terms to understand. The first one is lowering heat value. This is when water in the exhaust gases stays as vapor, so no energy is recovered from its condensation. The second one is the higher heat value. This is when the water vapor is fully condensed and the heat of vaporization is recovered. So the combustion equipment efficiency measure how much of that fuel's heating value is successfully turned into useful heat. For example, chamber, the combustion chamber has an efficiency of 70%. That means 70% of the heat from the fuel is used to heat for example, the car. For example, if it's car or if it's building, so how much the efficiency of it. And this is the equation you can see is the amount of heat released during the combustion divided by the heating value of the fuel burned. In this slide, we will talk about the overall efficiency of a power plant. But before that, let's define the generator. A generator is a device that converts mechanical energy to electrical energy. And for example, if you still remember the turbine, it has like if you have energy and if you have like a cycle and there is like solar energy or whatever, or and it's this energy expand the turbine to make it doing a mechanical energy. So to convert this mechanical energy to electricity, we need a generator. So this generator generates electricity. For the overall efficiency of a plant, it's measure how effectively the plant converts the energy in a fuel into usable electrical power. And it takes into account several stages. For example, the generator efficiency, which is how effectively the mechanical energy is converted into electrical energy by the generator, and the thermal efficiency, how will the plant convert the heat energy into mechanical energy to derive a turbine. And we can see the equation here. The overall efficiency of power plant will equal we have seen the efficiency of the combustion before in the previous slide, multiplied by the thermal efficiency, which is this one, multiplied by the generator efficiency. And we can say the rate of the work for the net work for the whole cycle for the electrical, divided by the heating for the higher heating value, multiplying by the mass flow rate of the fuel that we're using. And for this figure, we can focus on comparing the energy efficiency between compact fluorescent lamp, this one, and in incandescent lamp, which is this one. And we can see the 15 watt compact lamp is much more efficient than the 60 watt lamp, even though the second lamp will use 60 watt of electricity. The other lamp only needed 15 watt to provide the same amount of light, so it's more efficient than the 60 watt. In this slide, we will discuss the efficiency of the mechanical and electrical devices. The mechanical efficiency equation we can see here is the mechanical energy output over the mechanical energy input, and we can put it like E mechanical out divided by E mechanical in. Also, we can represent it as 1 minus E mechanical loss over E mechanical N. The effectiveness of the conversion process between the mechanical work and supplied or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiency. For the pump efficiency, we can see the mechanical energy increase of the fluid over the mechanical energy input. And we can say delta E mechanical fluid over we can say delta rate of energy mechanical fluid over the rate of work shaft N. Also, we can say the rate of the pump over the rate of the pump U over the rate of the pump itself. For the efficiency of the turbine, we can see the mechanical energy input divided by the mechanical energy decreases of the fluid. For the figure 2.58, it's an example of using the mechanical efficiency equation. We can see here is the fan, maybe it's fan turbine or whatever, and the air is coming in state 1, and the shaft will do the work like 50 watt, and the mass will be 0.506. This is the mass flow rate, so kilogram per second for state 2. And if we look at the for the mechanical equation, we can see there is no for the kinetic energy, V initial is 0 and V final is 12.1. For the potential energy, there is no potential energy and there is no flow energy or flow work. So we will left with this term multiplied by the mass flow rate, the kinetic energy multiply the mass flow rate over the work, the rate for the shaft work, and when we divide these by each other, we will get the efficiency is almost like 0.74, which is 74% efficiency. This slide shows the concept of combined efficiency for systems like turbine and generator. It shows how to calculate overall efficiency by multiplying the individual efficiency of the turbine and generator. The formula for turbine generator overall efficiency is given with example in this figure. When it says like pump turbine efficiency, it means for all of these devices or systems. So if we have the efficiency for turbine is 0.75, which is 75%, and the generator is 0.97, which means the generator efficiency is 97. So it means like this. So the equation will be the efficiency of turbine multiplied by the efficiency of the generator, and we will have 73%. For the last two slides, here we can just combine them together. These just figures related to the last part, which we will talk about the environment and the energy. Energy is really important in our daily lives. It gives us electricity for our homes and factories, plants, and power cars, buses, and trains. With energy, we can cook, we can keep warm and travel. It also has a serious effect on in our environment. The use of fossil fuel like coal, oil, and gas release harmful pollution into the air, leading to problems like acid rain, pollution, climate change. These pollution not only harm our planet but also affect our health. Therefore, using renewable energy should be encouraged worldwide to make our planet healthier. Improvement in thermodynamics have helped improve energy efficiency and reduce the pollution over years. Thank you, and sorry for the delay for recording this video.